Today we're going to take a look at section 9.9, and this is representation of functions by power series. And we're going to revisit a very specific series that we encountered quite early on in this semester, and that series is the geometric series. So we're going to start by looking at this. We're going to consider the function f of x equals 1 over 1 minus x, which closely resembles the sum of a geometric series that converges. So the geometric series, remember, looked like n equals 0 to infinity. We've got our a sub n, r to the n, and the summation, when it converges, was a over 1 minus r. So compare that to the f of x equals 1 over 1 minus x. They're close. And this specifically was only true that it equaled to this when the r value was strictly between 0 and 1, the absolute value of r anyway. So in other words, we could rewrite for a equal to 1 and r equal to x, we can say one over 1 minus x equals the summation from n equals 0 to infinity of a times r to the n. And specifically what that would look like for our values is that the a would equal to what? 1. I already wrote that down. I put it up here. A is equal to 1. So if you want to write the 1 in, you can. And r is equal to x. So x to the n, like that. And if I were to write these terms out, just a few terms just to remind you, we've got x, I said it right the first time, 1 plus x squared, and it would continue after that. I'll put plus dot dot dot. And again, this only works when the r value, which is now our x value, is less than 1. So absolute value of x less than 1. If the series is centered elsewhere, where is this series centered? Can you tell? More discussion last time?
0.
Yep, it's centered at 0. So it's centered at 0 because it just has x to the power of n, not x minus or plus something else to the power of n. So if it's centered elsewhere, you must develop a different series. Okay, so what we're saying is that there's this one very specific function, 1 over 1 minus x, that can be used, where we can use a geometric series to write it in a summation notation. And it's a very specific series. It's centered at x at c equal to 0. All these things are very specific. And the question is, well, if I can just do something for some other thing, how does that apply? Well, it's going to go back to this. So let me give you an example so you can see what I mean. So we're going to find a power series for the function centered at C. And our first one that we're going to take a look at is the function 2 over 6 minus x. And we're going to center it at C equal to negative 2. Okay, so I know this isn't 1 over 1 minus x, but 2 over 6 minus x, it's close. I mean, like I got some numbers that are wrong, but it seems like there should be some way that I can use the other information for this particular function with a little bit of manipulation. And I can. And we need to do some algebra manipulation, actually, to make it look like 1 over 1 minus x. That's our goal. The other issue is that we have it centered somewhere else. The previous one was centered at 0, and now we're centered at C equal to negative 2. So we're actually going to start with the centering and fix that part first. So we have our function 2 over 6 minus x. And what we really want is we don't want it to be x. We want it to be x plus 2. And the reason we want it to be plus 2 is because it's centered at negative 2. So minus negative 2 would be plus 2. Now the 6 at the beginning can't change and this negative can't change. But the negative that's in front of the x plus 2 now means that it didn't really add 2 to the denominator. What did I do? I subtracted 2. And so to compensate, I will add 2 to the end. Okay, does that make sense for everyone? This almost feels like when you're using completing the square on something. It's got that same kind of feel to it. Okay, so what we're going to do then is that we're going to combine the 2 at the end and the 6 at the beginning. So now I have 2 over 8 minus x plus 2. Okay, so I've got it centered in the right location now. That's the first thing we're going to deal with. The second thing we're going to deal with is that we really want it to say something else besides 2 and 8. I really want the denominator part where the 8 is to have a 1 in it. Okay, not a 2 in it. And I'm comparing it again back to this piece up here. Now the numerator being 1 or 2 or anything else is sort of irrelevant, not necessarily completely irrelevant, but you can see how we took care of that, right? This 1 right here and here became the A, and there was a 1 here. So whatever our number is on top, I can adjust for that quite quickly. But the 8 on the bottom, not so much. So we're taking a look at the number 8. So what we're going to do next is going to feel very much like what we have done before with limits. We're going to multiply by 1 over 8 because that will create the value at the beginning to have a 1. Now, does it mean I've got some 1 over 8s everywhere? Well, sure does. In fact, I've got a 2 on the top and I have a 1/8, so this is now a 1/4. And then right here, I've also now got the x plus 2. Oh, and I changed my sign accidentally. There we go. I've got my x plus 2 is now also over 8. Okay, did I get all my pieces in there right? Okay. So where are we? Well, at this point, we can actually identify what A is equal to. What is A? 1/4, yeah. And what is R?
X plus 2 over 8.
Yeah, it's the part that's at the end, the x plus 2 over 8. Okay, so we're making connections. Whoops. Trying to piece the pieces together in a reasonable way. And as we do that, that means we're going to be able to take this series that we've rewritten as 1/4 over 1 minus x plus 2 over 8. And we're going to be able to rewrite it in a geometric form. So it starts at n equal to 0 and it goes to infinity. It has a 1/4 for the value of A. And then for the value of R, I have x plus 2 over 8. It's 8, right? Yeah, 8. to the power n. But writing it in this closed form, right, saying that this thing that I've created over here on the right actually equals this quantity hinges upon the fact that the r value, which is now our x plus 2 over 8 value, is strictly between -1 and +1, right? This, for the geometric series, is only true if r is between -1 and +1. So we actually have to identify that that's the case. Otherwise, we're stating something that may not be true, and that's our problem. So this converges. I'm going to use another screen. This converges when that x plus 2 over 8 is less than 1. And we're going to simplify that inequality, find our actual interval of convergence, which is something we talked about in a previous lesson. So this is -1 is less than x plus 2 over 8 is less than 1. If we multiply by 8, -8 is less than or equal to x plus 2 is less than 8. And then if we subtract our 2, we're from -10 to 6. So our interval of convergence, I'm going to abbreviate it by IOC, is from -10 to 6. And we don't have to worry about endpoints. Endpoints for a geometric series are determined strictly with parentheses always, because it's always strictly between -1 and +1. So I don't have to test any endpoints. It will diverge on those endpoints. Okay, so if it has this very special form that looks like 1 over 1 minus x or a over 1 minus r, if you can get it into that kind of a form, we can make these appropriate substitutions. We can take a look at the interval. We can get a form for a power series representation. So we've seen some different operations with series along the way, and we have a few more that we're going to look at today. So these are operations with power series. So we're going to let f of x equal the summation from n equals 0 to infinity of a sub n x to the n, and g of x be represented by the power series, the summation from n equals 0 to infinity of b sub n x to the n. So two different power series, two different coefficients. All right, so the first one, these are going to operate very much like you would expect them to operate. If you multiply k times x, you're going to be, actually I think I'll give myself a little bit more space. You're going to be evaluating our function where it says x with kx. So you're just replacing the x with the kx. So we're at f, so this one right here. So this x gets replaced with kx. Well, when I do that, it means that I'm going to have the same a sub n at the beginning, but then now I have k times x to the power n, or if you prefer, you have k to the n, x to the n. It's exactly like you would think it would do, right? No different. The next one, I'm going to use the notation for your book. I don't like this notation, but we're going to go with it anyway. X to the capital N. Capital N is a constant. It's not something that's going to change. The lowercase n is varying as the n's go up. Do I wish it were a different letter? Yes, I do. But we're going to be okay. So this will be the summation from n equals 0 to infinity. And we're replacing the x with x to the capital N. So you have a power to the power, you end up multiplying the power. So a sub n, and then it's x to the n times capital N, or you could do capital N times n. So you end up multiplying the exponents. And the last one, which combines the two functions, does so with either addition or subtraction. And much like when you're doing derivatives or limits or anything else, we just combine them the same way. N equals 0 to infinity of a sub n plus or minus b sub n, because they're each multiplied individually by x to the n anyway. So we're just combining their coefficients. We're going to see number 3 at play specifically later today, and I'll try to make mention when we do it that's what we're seeing happening there. This can change the interval of convergence. So if you'll notice the original part that I described this as, they both started as n equals 0 to infinity. But if one of them started at n equal to 0 and one of them started at n equal to 1, or if the intervals, I didn't mean it that way, if the intervals on which they were defined were different, like these intervals are all surrounding with 0, but they wouldn't have to be, then we would be looking at the most restrictive amount of the series. So let me give you kind of just a general example of what I mean, so you can see what I'm talking about. Like if we had, for example, actually let me put that note in here just so it's written in your notes too. So note, this can change the interval of convergence, IOC. So if you had something, for example, this is n equal to, they're going to all be n equals 0 to infinity. If this were defined on -1 to 1, x to the n, but then we had another one that was defined on, say, -2 to 0, like this. It has to be the overlapping part of that interval, and where do -1 to 1 and -2 to 0 overlap? Sorry, that needs to have something in it.
-1 to 0.
Yeah, so, oh, I didn't think through clearly that. Okay, I was about to change something in my notes. I'm going to go back to what I have. It works better. -2 to 2, but I'll mention the one that Jubal just announced, which is what I was going for. All right, this one is actually defined on the interval -2 to 2. Then when we combine these, we could actually factor out the pieces that are being multiplied, like the x to the n is being multiplied by 1. And the x to the n in the second one is actually being multiplied by 1 over 2 to the n, like this. And we could combine them because they're both being multiplied by x to the n, but the interval is the restrictive interval, whatever -1 to 1 and -2 to 2 restricts to when you compare both of them, which in this case would be the narrower one, which is -1 to 1. But what I was trying to create in my mind, as I was saying it, is that if you have overlapping intervals, not just embedded intervals, it's still only the pieces where they overlap. So this is the intersection of intervals. Okay, so we're going to try some more of them like this, at least one more of them, where you can see how these pieces interplay. So I think these directions are almost the same as what we had before. Find a power series. And the interval of convergence. And this one's interesting. So they're going to give you something, and I'm just going to pause because this is perhaps a little alarming when you first look at it, because it doesn't really look like 1 over 1 minus x that I saw before, right? It doesn't. But they will define this for you and they will break it apart. So from Calc 2, one of the features that you might remember doing, and maybe it wasn't your favorite, but one of the integration techniques involves something called partial fractions. Do you remember that? So I'm not asking you to do the partial fractions, and your book isn't either in WebAssign. They're going to actually do the partial fraction breaking apart for you. And so the problem will actually start out looking like all of this. Like that. So they do the partial fraction break apart. And once they do, now you have two separate pieces that do kind of look like 1 over 1 minus r. In fact, one of them looks really a lot like it. And we're going to be able to use these different operations that we just saw to combine their expressions when we're done together. Okay? So we'll do them in order. The first one is the 1 over 1 plus x. But my form that I want is 1 over 1 minus something. So it's 1 over 1 minus what?
Negative x.
Yeah, negative x, right? If I make it minus, I'll make the negative a negative x, and then it's going to match. No problem. So we'll identify that my a value, well, the top value is still 1. But what is my r value this time? It's actually negative x. So as we're taking a look at this summation, we'll now have the summation. This will equal the summation from n equals 0 to infinity. And it's 1 times, I'll put it in just for the sake of it right now, 1 times, and then it's r, negative x to the n. Okay, so we want it to say something times x to the n by itself, and right now there's a negative grouped in there. And so just as a reminder, when I have negative, x to the n, what this really is it's negative 1 to the n and x to the n, right? So we can separate it out in that fashion, and then what kind of a series do we have? Yeah, it's alternating. So this is a summation from n equal 0 to infinity of negative 1 to the n, x to the n. So we'll come back to the alternating series component of that in a moment. Okay, the other one that we have is 1 over 1 minus x, which we've already looked at before. We don't have to do a whole lot for that one. It's a summation from n equals 0 to infinity, and it's just of x to the n, right? So we're going to combine these two things together. So my h of x that I was given to begin with, which was negative 2 over x squared minus 1, or 1 over 1 plus x plus 1 over 1 minus x. So if I look at that, I can now use the individual expressions that I just got in power series notation. So I have the summation from n equals 0 to infinity of negative 1 to the n, x to the n, plus the summation from n equals 0 to infinity of just x to the n. Okay, so this is what I was referring to when we looked at this number 3 over here. I have them both times x to the n, so I can pluck out their coefficients and combine them. So instead of having this all written in two separate notations, I can actually write it as negative 1 to the n plus 1 times x to the n. So you don't have to like the notation, but do you see where all the pieces came from? Okay, so if we look at it from a factoring standpoint, or we look at it from, like a generalized standpoint, there doesn't really look like there's a great way to combine the negative 1 to the n and the 1. However, if we write out a few terms of it, you will very quickly see that there is a very nice way that this collapses. So we're going to write out a few terms. We're going to write them out till I've got 5. So we're going to start with n equal to 0, n equal to 1, we'll do n equal to 2. I may need to go to the next page. I think I will. And then we'll do n equal to 3, n equal to 4, and n equal to 5. How do I know where to stop? As you start filling them in, you'll probably figure out where to stop pretty quickly. I just think that this is probably at least sufficient for us. It may be overkill. All right, so let's see what happens when I put in n equal to 0. So if I do negative 1 to the 0 plus 1, what will I get? 2. Yep. What if I put in negative 1 to the 1 plus my 1? I get 0. How about negative 1 to the 2 plus 1? I get 2. And if I have negative 1 to the 3 plus 1, I get 0. What's happening? 2, 0, 2, 0, 2, 0. And so even without finding them specifically, we know this is a 2 and then this one is a 0, right? We can figure that out. And if we're taking a look, oh, I'm off a little bit on my spacing. Sorry about that. If we take a look at the function itself that we were dealing with, we can rewrite this out now a few terms at a time. So we're going to do that. The first term is 2. The second term being 0 means it's 0 times x. Then we have another 2 times x squared, and then we have a 0 times x cubed. And then we have a 2 times x to the 4th, and a 0 times x to the 5th, and the process will continue indefinitely. Half of these terms go away, right? So I don't really have these here anymore because they're all times zeros. So let's see if we can find a better way of writing 2 plus 2x squared plus 2x to the 4th plus 2x to the 6th and so on. It's cleaner. Well, the first thing I notice is that they all are being multiplied by 2. So I'm just going to write it at the front. If you want to write it there, or you can write it inside the summation and write it over here, not in both places, but one or the other. Pick your spot. N equals 0 to infinity. What about the powers of x?
By 2n.
Yeah, they're 2n, right? They're all positives. I mean, not positives, they're all evens is what I meant to say. And 2n gives me even numbers. And I want to make sure that it's actually going to start at the right place. And starting at the right place has to do with where n equals 0. That's where n is starting. So I want to make sure I get the right term. So if I put in n equal to 0, I get 2 times x to the 0. Does that give me 2? It does. So this is going to work, or you can write it like this. Right? For our series. So that's the series part. We found the series, a nice condensed form of the series. But we need to find the interval of convergence as well. So what is my interval of convergence going to be for this one?
It'd be negative 1 to 1.
It will. How come, Jubal?
Because all you have is x is going to be the r value, same as normal.
Yeah, x is going to be the r value, same as normal. So it's just like for a geometric series, the r value is always between negative 1 and 1, and we don't have anything grouped with that x. It's not like x divided by something or x times something inside of the power n. None of that's going on. So my interval of convergence is the basic negative 1 to 1 that we have had before. Okay, is that all right?
Sure.
Sure. Okay, geometric series. We're going to do another type of integration, or another type of series notation today. It is integration and differentiation. So another method for finding a power series is by integration and differentiation. I'm going to abbreviate. Differentiation. Integration and differentiation. And let me show you how the problem starts every time. So the directions look just like what we had before. Determine a power series and interval of convergence. And our question will start out looking like this. F of x equals 2 over x plus 1 quantity cubed. And they tell us we're going to do the second derivative of x, second derivative with respect to x, of 1 over x plus 1. This is how it starts. They're not asking you to create that. That's the given question. So what are we doing? Well, if you take a look at what's in the box, it's a geometric series form, right? Not the box, but the brackets, right? So we're going to replace the part that's in the brackets with the geometric series in the power series notation that we've been working with. And we've already done this one once today. It was previous page right here. So 1 over 1 plus x is this alternating series form. So we're going to be able to just plop it right in there. Do not recreate work for yourself. If you do one place, don't go doing it again a second time. That's unnecessary. So I didn't mean to put equals there. I meant to put a bracket there. And we have the summation from n equals 0 to infinity of negative 1 to the n, x to the n. And this came from example 2. All right, so what is d2, dx2, what is the notation at the beginning telling you? Well, it tells you to take a derivative twice, right? So we're going to be taking the derivative of the summation from n equals 0 to infinity of negative 1 to the n over x to the n. So I've already written this down. That says d2x. There we go. And we'll do it one time, and then we'll have to do it again. So what is summation from n equal to 0 to, I'm sorry, we'll actually leave this off and we'll talk about that in a second. I've got my summation. All right, so the negative 1 to the n part, when you take the derivative of negative 1 to the n, it's just going to oscillate, right? So the n will come down, it's just going to, we're just going to end up oscillating our values here. They're not going to change. So it doesn't change when we take its derivative. But the value for x to the n will. So x to the n will become n times x to the n minus 1. Now I'd like for you to think about what happens when you take a derivative. When you take a derivative of, we'll just use a line as an example, y equal mx plus b. What happens to the plus b? It goes to 0, right? And when we plug in n equal to 0 in this equation, or this expression, this summation, we get the constant term. Right? So when we take the derivative of this thing, the constant term is going to become 0, which means our series will actually now start at n equal to 1, because at n equal to 0, the term goes away. It still goes to infinity, because you can't take 1 away from infinity or add 1 to infinity. That doesn't matter, right? We have to do it a second time. So we do this the second time, and there's no more derivative notation. I still have the negative 1 to the n part. I still have the n because it's a coefficient. And then I need the coefficient now that was the exponent, so that's n minus 1. I didn't mean to leave off my summation. I just meant to leave off the derivative summation. Just like last time, when I take the derivative, the constant term goes away. Well, the constant term now is going away from n equal to 1. So now I've got n equal to 2 here. We will fix the summation part at the end. It will go back to 0 in a moment. But for now, it's at n equal to 2 to infinity. And then this is x to the n minus 2. Everybody good so far? Taking derivatives. Changing my summation lower limit. But now I am going to go back to having my summation start at n equal to 0. How do I do that? Well, I just need to figure out what happens when n is equal to 2 so I can reset it. So if n is equal to 2, how is that different than what n is already? Sorry, my negative 1 to the n doesn't change, so let's just put that in there. So if n is equal to 2, what would I have to do in order to adjust that? Well, it will look like n plus 2, right? Because if I plug in 0, look at what happens here. If I plug in 2 right here, this n becomes a 2, right? But now if I change it to n plus 2, when I plug in 0, it still becomes a 2. Are you with me? I want to be able to plug in 0 into this expression and get the same value as when I plugged in 2 into the expression before. So what's the n minus 1 going to become? N plus 1. And again, you can check by physically taking the number 2. 2 minus 1 would be 1, right? And this one is 0. 0 plus 1 would be my 1. So you can just check it at the first value to make sure that it's right. What about my exponent on x? It will just be n. Right, so if I plugged in 2 to my exponent here, 2 minus 2 would give me 0. Now if I plug in 0 on the bottom one, x to the 0 is going to be the 0. So I'm resetting my expression. So you'll reset your expression each time. What's my interval of convergence? Still geometric series, so it's still, nope, there's not, -1 to 1, yeah, so yeah, I didn't mean 0. There, it's centered at 0, you're right, it's centered at 0, and then my interval of convergence is 1 on either side because my geometric series will only converge when the ratio r is between -1 and 1. Any questions on that? Okay, so I told you we were going to use integration and differentiation, and so far we've used differentiation, so now we're going to use integration. All right, so my last example, f of x equals the natural log of x plus 1. And the natural log of x plus 1 is the same thing as the integral of 1 over x plus 1. I don't think that's a stretch for you to know that those things are correct. But again, they're giving you that. They're not asking you to find the other notation. This is the given problem. That's actually really nice because after the integral symbol, that part we've already done. In fact, it was the one we just did from example 2 that showed up again in example 3. So it's showing up again. So we're going to take a look at this integral of the summation from n equals 0 to infinity of -1 to the n, x to the n. And just like with the derivative, where I can move the derivative through the summation, I can move the integral through the summation. So in a very real sense, actually I'm going to copy it and do it because I can. In a very real sense, what we're doing is we're shifting this notation. Right? That's what we're doing. So I want the integral of -1 to the n times x to the n. Well, just like before, -1 to the n, those are coefficients. So they're not changing. So this is still just -1 to the n. What's the antiderivative of x to the n?
X to the n plus 1 over n plus 1.
Right. And I need to do something else. I don't need to write my summation notation, but there's something else in terms of my integral that I need to do. Those of you who've been in to take your antiderivative test, it's already caught a couple of you. Plus c's, right? Plus c on the end. We will figure out what the c is before we're all said and done. So that's something we'll have to figure out. I still have the interval going from -1 to 1. This is still x to a power, right? So my interval still is -1 to 1. And we're going to solve for c. So to solve for c, notice the natural log of x plus 1 is now equal to the summation from n equals 0 to infinity of -1 to the n plus 1 over n plus 1 plus c. This is where we're at so far, right? These two things are equal. So in Calc 1, somewhere along the way when you first learned to do antiderivatives, what you saw is that there, sorry, I left something out, didn't I? X to the n got left out. Plus 1, n plus 1, yeah, sorry. When you were doing problems, they called them initial value problems. and they would give you a function, and you had to find the antiderivative, and you had the plus c, and then they would give you a very specific point somewhere along the actual curve so that you could figure out what your c value was. We don't need a specific point along the curve to figure that out. We can use any point that works. In particular, if you take a look at this function the way that it is, because it's natural log of x plus 1, x being 0 is a very nice value. So if I let, there's nothing special about it except that it's nice. If I let x equal 0, I actually have the natural log of 1 on the left. What's the natural log of 1? It's 0. And on the right-hand side, the summation from n equals 0 to infinity over here, I have negative 1 to the n, and then my x to the n is actually going to be 1, right, over n plus 1 plus my c. But this piece right here, if n is equal to 0, what does all of this become? I don't mean n. If x is equal, what does all of this become?
0.
Yeah, this is 0. All right, so this piece is actually equal to 0, so my c value is actually going to equal 0 on this. So even though I had the plus c at the beginning, c ends up equaling 0. I didn't write that well. There was supposed to be a 0 here. No wonder some of you are looking at me like I'm crazy. That's a 0. There we go. If x is equal to 0, that's 0. The whole thing is 0. Okay, so back up where we were. The summation, the natural log of x plus 1 is the summation from n equals 0 to infinity of negative 1 to the n, x to the n plus 1, over n plus 1. I don't have a plus c because the c is 0. The interval of convergence is a little bit trickier, though. So interval of convergence on this. So we know that it converges negative 1 to 1. I mean, like, that's true. And as a general statement, I have mentioned that because we're looking at geometric series, we don't have to test the endpoints. And that's also true. The difference is on this one, excuse me, is that if we look at the endpoint for x equal to 1, what happens to this function if x is equal to 1? It oscillates. It's a what kind of series? Well, what is this anyway? It's a what kind of series? It's alternating series. And since it's an alternating series, we actually are able to have the limit going to 0, right? And it converges. So I actually get to use the endpoint on this one, oops, where 1 is included. Negative 1 doesn't work, because if I put in negative 1, it doesn't oscillate anymore. I'm totally highlighting the wrong series. This is the series I was meant to box in. Cut that out, sorry. This series right here, if n is equal to, or not n is equal to, if x is equal to 1, this piece goes away, right? And I have negative 1 to the n over n plus 1. The limit goes to 0, and it's alternating. But if the n is, me and my words today, I'm struggling, I'm so sorry. If the x is equal to negative 1, then I would have negative 1 to the n plus 1, and I'd have negative 1 to the n, and they'd cancel each other out. They'd be alternating at the same time, right, the negative ones, and they wouldn't have any more alternating, right? It wouldn't be alternating. It would simply be 1 over n plus 1. Well, 1 over n plus 1 is practically speaking a harmonic series, right? And we know it doesn't actually converge. So it converges when I have the negative 1 because it alternates. It doesn't converge when I have the positive 1 left on top, that is, because I end up with a harmonic series. So the interval of convergence on this one actually does include this endpoint. Over here, you might look at this and say, well, why don't we have to check and make sure none of that happens over here? Because it is an alternating series. And the reality is we should, and I didn't on purpose because I knew I was going to come back to it and mention it, okay? The reason it doesn't matter here is because here, this x to the n, I'm sorry, not that piece, this n plus 1, if x to the n is gone away, n plus 1 and n plus 2. These two, the n plus 1 and the n plus 2, they go to infinity. So it doesn't matter whether it's alternating or not, right? The limit's not 0. Whereas on the one over here, if I don't have this piece at the end, the n plus 1's in the denominator, and it's going to infinity, which makes the whole thing go to 0. So on this one, the alternating series had a limit when it was alternating going to 0. And on this one, it didn't. This piece goes to infinity anyway, so it doesn't matter if it's alternating or not. It's still not going to converge. Okay, aside from my misspeaks throughout the entire lesson, are we okay? Okay. All right, let me write up the homework, put it on the sheet. It's shorter, so I'm sorry that there's not a lot of time for board stuff today or anything, but there will be next time. I already told Hannah about this, so I apologize, but it's page 666. It's number 4, 7, 10, 13, 20, 21, and 24.